The role of autonomous vehicles in combat situations is expected to grow significantly in the near future. Our client, Advanced Vehicle Systems Defence Science and Technology, DST, conducts research and development of such technology for the Australian Army. Testing autonomous technology in the real world is costly and unsafe, so DST has sought another approach. Over the last 2 semesters, our group has designed and implemented a virtual testbed for DST that can simulate the resultant behaviour of autonomous vehicles using ROS and the Unreal Gaming Engine. The accuracy of our simulation is dependent upon the realism of the environments, so a large amount of focus went into designing the maps. Creating an environment from scratch required us to learn tools such as World Machine and the Unreal Engine blueprint system to create materials. Our main difficulty was finding free, high-quality textures and materials that blend together well, such as trees and rocks. We overcame this by reusing our available assets to create a terrain that was a balance of realism and practicality. A great deal of thought and planning went into creating our user interfaces. The flow of menus was carefully considered to ensure that it would be intuitive to users of any experience level. The challenge for our developers was coordinating the user interface design with all other areas of the program that are dependent on its functionality. To enable users to simulate multiple scenarios, we needed a mechanism to customize the locations of agents on the map. This required some user interface design so that users could select spawn points at multiple predefined locations. Then upon commencement of the scenario, the game object positions are updated to these locations. Both allied and enemy agents need to be able to coordinate their intelligence to perform effectively. Operating in a fleet mentality requires a method of radio communication between allied agents. The physics of radio propagation is extremely complicated, and simulating that would be equally as difficult. To save program performance and development time, we have opted to use propagation models which are based on empirical evidence rather than precise calculations. A major benefit of holding experiments inside a simulation is that it provides easy access to lots of important data. With multiple complex data streams for all parts of the simulation, collecting this data is no small task. Leveraging the power of polymorphic design, we created a modular recording system capable of recording any data type from anywhere in the solution. Although this program was created with an intention to allow DST to implement their own machine learning algorithms, we are required to provide placeholder AI that can demonstrate the program's capabilities. Our AI needs to be sophisticated enough for our agent to defend itself from attacking enemies. This requires using camera and laser sensor input to identify potential threats and anticipate their assault. The AI also needs to have a strong awareness of its environment so that it can take effective countermeasures to protect itself. It does this by mapping its surroundings. Once it has made a decision, it sets a series of movements to be performed by the agents. The final goal of our project was being able to replicate the results of our simulation in the real world. For this purpose, we have acquired a small robot from DST called a Jackal that is equipped with cameras and uses the ROS middleware for logic and control. We used a plugin for Unreal Engine 4 that compiles and translates messages between C++ and ROS. This integration means we can send environmental input from our simulation to the real-world Jackal that's identical to what it would receive from its onboard cameras. The effectiveness of our simulation will be confirmed by testing the Jackal's responsiveness to a real-world assault.